This is the 14th video in the series on the Control101 MATLAB toolbox, and here we're going to look at lag compensator design using frequency response methods. So the community has agreed on an outline structure for a Control101 course, and this toolbox has been developed to support such a course because MATLAB tools enable visualization and support tedious number crunching so students can focus on core concepts. This video is going to focus on introducing the concept of lag compensator design using frequency response and Bode plots. Now a reminder, CISO tool is excellent for this in general, but is somewhat more complicated. So this toolbox app is deliberately a bit simpler, so students can focus on one thing at a time and see the core parameters and specifications clearly while doing their design. A reminder of some technical background then. It's common to use phase margins and crossover frequencies to underpin frequency response design. So you can see the phase margin here, the crossover frequency, and the values if you need them. Typical design requirements then. We might use things like a maximal allowable overshoot, but equivalently in frequency response, we'll use the phase margin. We might be interested in the rise time or the bandwidth, and so equivalently, we're going to use the gain crossover frequency. And similarly, we're interested in offsets to steps and ramps, which is equivalent to a low frequency gain criteria. So the simple gain design, which we did in the previous video, illustrated that we can only meet a single criteria because we've only got 1 degree of freedom. And usually people aim for the phase margin as a simple criteria. In order to tackle further criteria, we need to introduce a dynamic component to our compensator. So for a lag, this component looks like this: k times s plus beta a over s plus a, where beta is bigger than 1 and typically less than 10. And what this will do is it will increase the low frequency gain by a factor of beta. A key thing to note is we use the same k that we got from our simple gain design. So how do we introduce our low frequency gain criteria then? Well, you can find offset to ramps using this formula here, shown in the red, which gives you a criteria for beta, or you can find offsets to steps. And for both of these, essentially, you can choose beta to achieve the desired offset. You set the offset, solve the formula to get the required beta. And again, you'll notice we're assuming that k is already known because you chose that using a phase margin criteria. What about the pole and zero positions then? In order to ensure the negative phase characteristic does not interfere too much with the phase margin you achieved with your proportional design, we use set formula for the poles and zeros, so there's no flexibility here. You have to choose these values. So you'll see the zero is chosen as omega c over 10, and the pole is chosen omega c over 10 beta, where omega c is the gain crossover frequency you got from your simple gain design. Now within the app, it will determine these values automatically and insert them for you. You don't need to do the computations because it already knows. So here's an illustration of what a simple lag compensator will look like. You can see it's got this characteristic phase dip, which is well to the left of the gain crossover frequency. The gain crossover frequency being marked with this solid purple line. And you'll see at low frequencies we've got some gain recovery compared to if we just had a gain. Okay, the purpose of the app then is allow students to practice and familiarize themselves with this simple lag design procedure. So step number 1, choose the gain to meet a specified phase margin. And this is the same as the proportional design we covered previously. Second, choose beta to achieve the required low frequency gain. Now the app will only allow integer values of beta because the focus is on understanding core principles, not doing a design down to 3 decimal places. Let's show you the app then and see how it works. So we've opened it up and we've got a default system in here. Okay, so let's choose a slightly different default system. Let's choose this one for example. Okay, and what can you see? you can see that the current phase margin is not particularly good. The current closed loop behavior is a bit oscillatory, etc., etc. So first thing I might do is actually go to this top left plot where it says overlay several KP. So what I want to look at is what happens as I change KP. So you can see changing KP changes the gain plot, as you see in this top plot here. So I've given lots of different values from 2 all the way down to about 0.1. And you can see here the corresponding phase margins that you get. So if I choose KP equals 0.1, I get this large phase margin. KP equals 0.2, I get a phase margin which is pretty close to what I want, this target phase margin. KP equals 0.4, the phase margin is too small. So from that overlay button, I can very quickly see I want KP about 0.2. So let's try that. So the slide is not very precise, but I've managed to get 0.2. And you can see now the phase margin is pretty much what I want. So that's step number 1. You do your simple gain design. Now, the second part of the design is to meet your offset criteria. So if we look in this bottom right-hand plot, you can see the dashed green line shows you that the offset that you want to achieve. So you want to go above that green line to be as close to 1 as possible. So how do I get closer? Well, I need to introduce a pole-zero ratio which is bigger than 1. So let's try 2. And you'll notice the app has automatically allocated the pole and the 0. It says, I know the gain crossover frequency already. I know that the 0 must be a decade away from that, so I don't need to ask you where to put it. I will decide for myself. So the only thing you need to choose is the beta, this pole-zero ratio. So I've used beta equals 2. Have I now met my offset criteria? And you can see, well, not quite. Let's try 3. Now, I'm not using formula here. As you saw in the earlier notes, you can use formula. You can work out a specific value for beta. But the purpose of this app is to allow the user to explore. You can see as I change beta, basically we get better and better offset. And you see the offsets are defined over here. Currently, 0.2 with just proportional, 0.0476 if I use my lag. Okay, so what's your offset criteria? And you can basically get a beta that will get you there. Now, clearly, as ever, you can look at lots of other systems. All right, as you please. Here's a totally different system. So again, do your overlay several KP, decide what KP you think you're going to want. So probably something along the lines of 0.3. Let's try that. Okay, that's not far out. Okay, I'm not being overly precise. So that looks about right. So now, actually, with our beta of 0. I forgot to set this to 1. Before you do the overlay, you should set your beta to be 1. So let's just check that didn't corrupt things. No, that looks fine. So still, I think the 0.3 is about right. Okay, so yes, I should have reminded you of that. It's really important. If you're going to start a new design, always set the pole-zero ratio back to 1 before you start, so it doesn't corrupt the other plots and the things that you're looking at. But thereafter, you can go through the same steps again. So you can see gradually increase beta until you get the offset down to the level you want. So some conclusions. We've demonstrated how to run and use the lag design phase margin app in the Control101 toolbox. This can be deployed during lectures and student private study to help students appreciate and relate their technical and analytical learning to authentic systems. And the manual contains links to some individual MATLAB source code that can be used as templates for individual investigations and modifications, should you need that. And again, a reminder that once you're confident in the principles, then tools like CISO tool might be quite useful because they're a bit more flexible and powerful.